Okay, so do you have any question from the last part of the discussion?
Excuse me, sir.
Hmm?
So for the first part of the lecture, the recording was saved in my drive. Can I upload it on the classroom portal?
Yeah. You can. So that is what actually I noticed that. No. Actually, the thing is that what I noticed is that only the. I mean, I have also seen that only 20 minutes of the first part of the lecture has been recorded. I
Yes,
don't
sir.
know,
The recording got stopped for some. So I guess what I received it that is of about 50 minutes.
about 50 minutes. So yeah, you can upload that. Yeah,
Okay,
you
sir.
can upload that. Yeah, so I in my app actually I received an email that says that only 20 minutes of the lecture has been recorded. But so if you have the 50 minutes version, then you can upload it.
Okay, sir. Sure.
Okay, so let us start again. And I heard that some of you have some other commitments today. So let us start and try to end the session as early as possible. Okay, so what is the advantage of this relations? Let us try to understand with the example of a realistic thermodynamic system. Okay, so let us start with the system of ideal gas. This is our favorite system, favorite thermodynamic system. Because so I have a thermodynamic system. Ideal gas. And as you know, the thermodynamic coordinates for this system is nothing but the pressure, volume, and temperature. So these are the thermodynamic coordinates, macroscopic coordinates you need to know in order to specify the thermodynamic system of ideal gas. So our objective is to understand how we can do some experiments. So that is the basic objective of thermodynamics. Do some experiment, and from the result of those experiments, you want to understand or you want to model, do a mathematical model for the properties of this system. So for that actually we will be using the equation, we will be using the relation involving the partial derivative, so what we have just discussed in the earlier class. So in the context of this system of ideal gas, you know that there exists a relation between P, V and T. There exists some functional relation. This kind of relation exists, and that relation we know it as the equation of state for the system. I have not discussed equation of states yet, but you know that there exists a relation. So we have already discussed that T can be written as a function of P and V. So there exists some kind of a relation between these three thermodynamic variables P, V, and T. So the partial relation involving the partial derivative, what we have obtained in the last session, is applicable for this P, V, and T. If I write down, I can write down that in this form. So I can write down del P by del V at constant T, del V by del T at constant P, and del T by del V at constant V should be equal to -1. So this is the easy. I mean, I find it easier to remember the relation in this form. So that's why I write down the relation in this form. So you can write down the second relation in this form. Now you can invert this. You can take this del T by del P at constant V from here to here. You can remove that. So this will be minus del P by del T at constant V. So this is the relation you know for an ideal gas. I mean, this is just coming from the fact that we are not assuming anything. Okay, nothing has been assumed about the properties, about the particular details of this system. Only our assumption is that, not the assumption, we know that we have already established from the zeroth law of thermodynamics is that this temperature T can be written is basically a function of P and V. So you remember that we have derived that function H, which is the function of X and Y in this case, P and V, and we call this function as this empirical temperature T. This is just the thing we are assuming in order to write down this relation. As long as there is a mathematical relation involving P, V and P is there, we can write down this relation. Okay? Now what is the advantage of this relation? I mean, what we are gaining from this relation? So we can do some simple experiment to measure these quantities. I will come to that, how to measure these quantities. You can think of simple experiment to measure these quantities. Actually, these quantities have some name. This quantity is called, I mean, this quantity is related to isothermal compressibility. Which is defined by this parameter called kappa, which is nothing but minus 1 over V del V by del P at constant temperature. So you see that this is basically nothing but 1 over V by kappa. Sorry, 1 over kappa V. This quantity is nothing but 1 over kappa V. Okay. Then you can define another quantity which is called volume expansivity. Which is defined by this quantity called beta, which is nothing but 1 over V del V by del T at constant pressure. Okay. So now, this is the definition of kappa, which is isothermal compressibility, and this is the definition of volume expansivity, which is the beta. This is the definition of kappa and beta, some parameter. At this point, remember that I am defining some parameters. Now I can easily multiply this equation with a V and divide this equation with a 1 over V and take this negative sign from here to here. Okay, now you see that this quantity is nothing but 1 over kappa, and this quantity is nothing but beta. So this you can write down as beta by kappa. Now what are this beta and kappa? I have defined some property of this ideal gas. Beta and kappa. Beta is basically the isothermal compressibility and kappa is volume expansivity. Now we can do some simple experiment to measure this quantity beta and kappa for a given system of ideal gas. Right? You can easily do an experiment. I mean, you can what you can do is that, for example, I can design a simple experiment. I can have a cylinder full of ideal gas. Okay, this is the cylinder. This is in thermal contact with a reservoir at a given temperature. This is the reservoir at a given temperature. This is the cylinder. This is my system. This is the surroundings. Surroundings is the reservoir at given temperature. So that will fix the value of, there are some weights on this cylinder. Okay, so this reservoir will fix the value of temperature. So I have to calculate what is del P by del P at constant temperature. So that means how much volume is changing if I change the pressure little amount. So that is what I have to calculate for a given temperature. So since I immerse this cylinder into a reservoir, so that the temperature is fixed, temperature is not changing. I have some weight, I know what is the pressure, I can calculate from the mass of these weights, I can calculate what is the pressure of this cylinder, I can also calculate what is the volume of this cylinder. So everything is known, P and V is known. I can measure the P and V, pressure and volume. Now, if I increase the weight by an infinitesimal amount, small weight, I put an additional small weight on this piston. So what will happen? This piston will go little down. Okay, so P will change by amount delta P. That will depend on this small weight which I can calculate. And volume I can measure. Volume will go little bit down, so I can also measure what is the change in delta P. So I can calculate what is delta P, what is delta P by doing this simple experiment, and from there I can calculate what is the value of kappa for a given system. Okay. Similarly, I can do the same thing for calculation of beta. In this case, I will do the system in a reservoir, same thing. But in this case, I will not change the weights. I will whatever weights is there on the piston, I will keep them as it is. Okay, but I will increase the temperature T of this reservoir to T plus delta T. Wait sufficiently long time so that the system comes to an equilibrium. So I know the pressure is not changing since I am not changing the weight. So the pressure of this piston is not changing. Pressure is fixed. Temperature is changing from T to T plus delta T. So that will the volume of the system will change. It will increase or decrease, whatever. There will be some change of volume. So I can measure the change in volume as I change the temperature from T to T plus delta T. So I know what is delta P, what is delta T. So I can calculate what is the coefficient of volume expansion. So these are the simple experiments what I can do to estimate these parameters. Now what I am gaining from these estimates, from these parameters. So that is the important question. That what is the advantage of having this? So let us do some little calculation. So I can write down my dP, change in pressure. Pressure is a function of, since there is a relation involving P, V and T, so pressure, I can assume that the pressure of this gas cylinder is a function of volume and temperature. So dP can be written as del V by del P at constant temperature dP plus del V by del V by del T at constant P dt. Sorry. This thing. So pressure is a function of volume and temperature. So del P by del T at constant volume dt plus del P by the volume and temperature del V at constant temperature dt. Right, so I can write down this differential relation. It's simple. These are very simple things. You need to be careful. Only thing is that you need to be careful. Which are the dependent variable, which are the independent variable. You should have a very clear idea about what you are doing. Otherwise, I mean, these things are very simple mathematics. Now we look at this quantity. Del P by del T at constant V. This is nothing but beta by kappa. Okay? So I can write down my dP as beta by kappa dt plus, now what is this quantity? Del P by del P at constant T. So this is nothing but 1 over kappa. See, del P by del P at constant T is minus kappa V. So if I invert that by using that law what I have just derived, So del P by del V at constant D will be nothing but minus 1 over kappa V dV. So I obtained this relation. This is interesting. I will come to that. Why this is interesting. This relation actually tells you that if you change the temperature of the system by delta T amount and volume of the system by delta V amount, inferential amount, how the pressure of the system is changing. Because you know this beta, value of this beta and kappa and the volume, you have already measured them from by doing different experiments. So this relation actually tells you how your pressure of the system will change if you change the temperature by delta T amount and volume by delta V amount. Okay, so that will give you some power of predictability. So you do some experiment and you do some mathematical modeling. So these are the mathematical modeling what I am doing. I do some experiment. In that mathematical model, I need some parameter to know. So these beta, kappa, these are the parameters which I measured from different experiments. Now once I have measured from different experiments, I know the future behavior of the system. Now if I ask, let me give you an example. If I ask the following question, let us assume that I have two heat reservoirs. Okay, two heat reservoirs, one at temperature T initial and another at temperature T final. Okay, I take a system of ideal gas and put the system in contact of this reservoir. The piston here, it's an adiabatic piston. I mean, all other parts of this cylinder is adiabatic. Only it can interact thermally with this reservoir, heat reservoir through this surface. So all these surfaces are adiabatic surface. Only this system can interact with the reservoir via this surface. Okay? And the volume is fixed. This piston is unmovable, so the volume I cannot change. So the state of the system can be written as initial pressure Pi. So if we wait sufficiently longer amount of time, this reservoir will equilibrate, thermally equilibrate with the system. So the temperature of the system will be Ti, and the volume is some fixed volume Vc. So this is the state of the system. Now if I remove the system from here and put the system here, same system. The volume is fixed. So what will happen? The system will thermally interact with this reservoir at temperature T if I wait sufficiently larger amount of time. The volume is not changing, volume is fixed. So if I wait sufficiently larger amount of time, the temperature of the system will become Ts and the pressure will change, Pf. This will happen. Now if I ask the following question, what is the change in pressure? What is Pf minus Pi? Change in pressure of this system. I can give the answer because I know this is the change in pressure dP as the temperature changes dt. Now here the temperature is changing from Ti to Pf, volume is not changing, so that dB is equal to 0. So this will not be nothing but integration beta by kappa dt Ti to Tx. Right? So you know the power of this technique. So we mathematically formulate a system. We do some mathematical formulation for the system, and that formulation is based on some general idea. I mean, I do not know what is the exact relationship. So I have assumed that there is a relationship between PV and T. Right? For ideal gas, you actually know what is the ideal gas equation. But in this calculation, I have not assumed any particular relationship between P, B, and P. I only assume that there is a relationship. So that assumption actually gives me the freedom to formulate the theory, do some experiment, measure some parameters. With that measurement, I have the power to predict the future behavior of the system, to predict the output of some experiment. If you do this experiment, you will have a prediction. And theoretically, you will, from thermodynamics, theoretically, you will get a prediction. You can check that prediction with the experimental result. Now, this beta and kappa, if this temperature is Ti and Tf, we do not know about how this beta and kappa depends on temperature. We do experiment at a given temperature, measure the value of beta and kappa. There may be some temperature dependence on beta and kappa, temperature dependence of beta and kappa. They may depend on temperature. Okay, that also we can find out. We can do this experiment which measure beta and kappa at different temperature and find out the value of beta and kappa as a function of temperature. So that we can do. Let us assume that if Ti and Tf are not very different, let us assume that in this temperature range the variation of beta and kappa or which temperature is negligible. Then this quantity can easily be written as beta by kappa Tf minus Ti. If I take a material, if I take some material, this is for ideal gas system. If I take another system, another thermodynamic system, where this expansibility beta kappa, they are function of temperature, then you need to know the functional form of beta and kappa and do this integration over temperature. Okay, but that is also possible, right? There is no difficulty in doing that. You need to know how beta and kappa varies with temperature from your experiment. The important point is that whatever we are doing, we are observing and we are measuring beta and kappa from our observation, from the experiment. Once we have the knowledge of beta and kappa, then we can predict the future behavior of the system without assuming any deep understanding or any specific understanding or any detailed understanding about the system. So this is the beauty of thermodynamics. So you do that. You do these things, and in the next course in statistical mechanics, you will calculate. You will actually estimate what is the value, what is the expression for beta, what is the expression for kappa, and all these things from a more fundamental theory. But here we are not doing that. We do experiment. We calculate beta and kappa and predict the behavior of the system. So this is what is known as what is called. So I have not explained what is the phenomenological model. So this is what is the phenomenological model. Phenomenological model means we do some observation, we do some experiment. From the experimental result, we try to fit the experimental result. We postulate some new laws in order to fit the experimental result, and that gives us some more prediction. So this is how a phenomenological model has been developed. This phenomenological model has been developed. This is a particular example of how you can get some new information about the system by just doing some mathematical modeling of ideal gas without assuming any details about the system. This is just a black box. I only know only details. I assume that there is a relation between P, B, and D, and that is also a consequence of another experiment, which gives you the zeroth law of thermodynamics. Clear, right? So I will talk about another example, and then I will go to the next part. So there are several examples in this in the book by Zimowski and Dickman. So you should read, you should understand. I mean, the philosophy is same. Only thing is that different systems need different thermodynamic variables, and so you need different coefficient. There are different coefficients which you should know in order to explain the system. But the philosophy is basically this. This is the philosophy. I am not going to discuss all this system, but you should learn, you should study all the system, whatever have been given, what are the possible thermodynamic system, the properties have been given in your book. This is in chapter 2 of this Zimowski book. Okay, so the next system I am interested in, that is a stretched wire. us draw a setup. Let us assume that I have a rigid wall here. Okay, so I have a wire. Fixed one end of the wire is fixed in this rigid wall. So this is my wire. This is connected to another wire which is not a part of the system. There is a pulley and I can hang a weight from here. So this is my system. Okay. So what are the thermodynamic variables in this system? So first one should be, so the equivalent of pressure for ideal gas in this case will be the tension of this wire. Tension means, so what is the force acting on this? So there will be a force acting on this wire. So that is the tension. So you have studied this kind of problem in your mechanics. So the picture is clear to you. Let us assume that this is X. Then second is the length of the wire. Let us assume that length of the wire is L. And third quantity is obviously, since we are studying the thermal properties, the third quantity will be temperature. Okay. So you can start from the same equation. In the context of this wire, the equation can be written as, so del F by del L at constant temperature, del L by del T at constant tension, del T by del F at constant, so del T by del F at constant length should be equal to -1. Do the same thing. So you can write del T by del F, sorry, del F by del T at constant length should be equal to minus del F by del T, minus del F by del L at constant temperature and at constant tension. Now, once you know these two quantities by the same analogy, you know that you will be able to find out the future behavior of your tension with temperature or whatever you want to do. So you need to know these two quantities. Now I do not know. You are already familiar with this quantity, right? So have you learned something called Young's modulus?
Yes, sir. We know.
You know that, right?
Yes, sir.
Yeah. So you can see that this is nothing but Young's modulus with some constant, multiplicative with some multiplicative constant. So Young's modulus, definition of Young's modulus is, so that is L by A del F by del L at constant T. Right? So this is related to Young's modulus. You do an experiment, measure your Young's modulus, and this is nothing but linear extensivity. So some kind of linear extensivity, some parameter. What is called? This is linear extensivity. Yeah, so this is actually defined as 1 by V del N by del T at constant. So if you increase the temperature of the wire, how the length changes? So that is the linear expansivity. So you can also do another experiment to measure the linear expansivity. Once you have the values of these two parameter measured, then you can calculate different other properties of this straight line. If you ask something, given that this and this quantity are measured, you will be able to tell what are the other parameters, other properties, how this system will vary with the variation of any quantity. I mean, F can vary, temperature can vary. How the system will vary as I vary the tension or temperature. Okay, so this is the example of straight wire. Clear, right? Everyone understand what is the, I mean, what I am trying to say, what I am trying to motivate. My objective is to motivate you about, I mean, what is the importance, what we are actually going to do. See, these problems are simple. Whatever I am discussing now is simple because this kind of quantity, this tension, length, temperature, or in case of ideal gas pressure, volume and temperature, these things you can visualize. You can easily measure these things. You can understand that what is the quantity, what kind of experiment we can do. So these are easy in that sense because you can visualize this kind of quantity. But as long as, I mean, as soon as we are going into the deeper thermodynamics, then we will be introducing new quantities which are more abstract. Okay. For example, internal energy, temperature, internal energy, entropy, enthalpy, this kind of different kind of similar kind of quantities, right? Which will be more difficult to visualize. So the important thing is that at this point you understand this subject, you understand the motivation of this subject, what we are trying to do. So these actually give you the motivation of this subject. We will be doing the same thing for the rest of this course, but in terms of some more involved, more intuitive, more abstract quantities. Okay, so we will be discussing in different contexts. We will be defining different quantities, their differentials, how they changes with different parameters, different thermodynamic coordinates. We will be doing these things for the rest of this course, but those will be more abstract. The construction of those quantities will be more construct. So at this point, it is important for you to understand that what is the philosophy behind defining these things. Young's formulas, this volume expansivity, all these quantities you can easily understand. Okay, so this is, I mean, this is the two example I do from Zimonsky book, but in Zimonsky book there are other examples. I expect you to read all those examples, and they are basically same. The philosophy of those examples, all these thermodynamic systems are basically same. You are expected to do read all those examples, do mathematics. Okay, so let's come to the homework. Okay, so I have finished 2 chapters of Zimonsky. So your homework will be to do the problems of those 2 chapters. Okay. So you do not need to send me your homeworks because it is not possible for me to check these copies. But it is expected that you will be doing all those homeworks, and some of the questions in your exams will definitely come from those problems. Okay. And I will make another set of homework set for you, which will, I mean, beyond those two, I mean, beyond the exercise of Zimonsky, I will make another set, another homework set, and I will send you. But those are necessary. I mean, those are mandatory that you finish those 2 chapters, the exercises that was given in those 2 chapters. Okay. Some of the questions will definitely come from those 2 chapters, and as soon as you finish those 2 chapters, the exercises in those 2 chapters, you will have better understanding about these topics. And if you have any questions about the problems in the book, in the homework, then you can discuss. We will definitely discuss. Okay, let's go to the next chapter. What? So you are all familiar with watt, right? Mechanical watt you have already calculated. I mean, maybe it has been several years that you are calculating what are the mechanical watts. What are, I mean, how to calculate? If you do apply some force on an object that moves, then how much watt has been done by the force or against the force? These are the things you have already calculated. I mean, it has been several years that you are calculating this kind of. So simply mechanical watt. So if I have a particle at point A, I apply a force F on this particle. It goes to another point B, the watt, and this displacement is d vector. The watt is nothing but F dot B. This is the mechanical watt. But we are talking about watt on thermodynamic systems. So we will discuss that. What is watt on thermodynamic system? Before going to the watt on thermodynamic system, so they are different. I mean, if you consider a thermodynamic system, that thermodynamic system, I mean, what you can consider watt in different contexts. For example, I have again a cylinder of gas. There is a piston here. So if you want to keep the piston fixed at this point, you need to apply some force on this piston. Let us assume that there is another piston. Here, there are two systems, system A and system B. And as a whole, this is my thermodynamic system. A plus B is my thermodynamic system. There is a piston here. Now, if the pressure balance of between system A and system B, the pressures in both the sides of system A and system B are not same, then what will happen? Common sense tells you that this piston, what is in between this system A and B, they will move, and at some point of time, they will balance the moving of this piston will balance the pressure between A and B, and the system as a whole will come to the equilibrium. Okay, so this is one kind of one. This kind of what we call the internal one. I mean, this is a simple example. Okay, so there are other internal watts which are more complicated. So this is a simple example of an internal one. My system is A plus B. So whatever happens between A and B, or then A performs some work on B or B performs some work on A, I am not interested. So this is the internal watt on which in thermodynamics we are not interested. Okay. If the system, some part of the system do some work on other part of the same system, I am not interested. We are not interested on those kind of work. This is a simple example. I mean, this is a raw and simple example. There would be other things, other complicated things. So internal work is going on inside the system. The point is that we are not interested on those kind of work. We are only interested on the work when this final piston is moving. We do some work, this external force is doing some work on the system, or the system is doing some work on the surroundings. We are only interested in this kind of, so internal work on which we are not interested in thermodynamics, and there will be external work. This is actually on which we are interested. Okay. So we are interested on external work. We will try to calculate how, I mean, how you can calculate the external work on this system. Some external force is doing some work on the system, so that is our point of interest. So before going further, you know that the sign of the watt is important. Okay, so in this definition, actually, this is very clear. The watt could be positive or negative, depending on the direction of displacement and force. If the displacement and force are in same direction, we say that the work is positive. If the dependence, I mean, if the displacement and the force are in opposite direction, we say it's a negative. Right? So this is quite clear in the context of mechanics, but also this is a convention. I mean, you choose to define what in that way. But this is the convention. In thermodynamics also we will define, we will choose the similar kind of convention. Okay. We will call, so let us assume that we have a thermodynamic system, ideal gas. Some words are there. Okay, so that means that external force is pushing this piston downside. So this is the direction of external force. If the system is in equilibrium, there is a pressure on this piston. P times A force is acting in the direction opposite to this external force, and they are balancing. So basically, you say that PA equal to F. A is the area of the piston, so this is how the force is balanced. So the point is that the direction of external force is in this direction. We will follow the same convention. I mean, about the sign of the thermodynamic work. So the convention will be, sign convention will be positive work will come. Positive work, I mean, by means of positive work, we mean that when the displacement of this system, of this piston, and the force are in same direction, then we will call it is a positive work, or work done on the system. Okay, so this will be our convention when the displacement of the piston and the force in the same direction. So that is the positive work. That is the definition of positive work. This is often called as work done on the system. And negative work is the opposite. When the displacement of the piston, in this particular example, when the displacement of the piston and the force, external force acting on the piston are in opposite direction, that means this piston moves upward. If the pressure inside this container is bigger than the force acting external force, then the piston will move upward, right? Move upward. So that kind of what we call negative work. This is often called as work done by the system. This is important, on the system and by the system. We will be using this word frequently. So you need to understand what do we mean by positive work, negative work done on the system, and work done by the system. Okay? So this is the sign convention, what we will be following in the rest of this course for work done. Now the next thing you need to understand is quasi-static process. What are the kind of process we are considering? We will be considering quasi-static. So what do we mean by a quasi-static process? So the equilibrium we have already discussed. A system is in equilibrium means that it is in mechanical, thermal and chemical equilibrium. Three kinds of equilibrium I am talking about. So equilibrium we have already defined. It should be mechanical. I will discuss these things in one or two lines. Thermal and chemical. So we have already discussed these things: mechanical equilibrium, thermal and chemical equilibrium. Mechanical equilibrium tells you that the forces, the external and internal forces acting on the system are properly balanced. There is no unbalanced force. If there is any unbalanced force, then the system will undergo changes, undergo through a non-equilibrium states as long as the forces are not balanced. Okay, so in order to ensure the mechanical equilibrium, what we need to ensure? We need to ensure that the forces that is acting on the system are perfectly balanced. If the forces are balanced, then the system, we can call that the system is in mechanical equilibrium. Similarly, thermal equilibrium. Thermal equilibrium tells you that if the system is thermally in contact with the surroundings, then it should have same temperature. There should not be any temperature difference. As soon as they are not, as long as there is a temperature difference with the surrounding, then the system will undergo heat exchange, and the temperature of the system will not be uniform, so the system will not be in thermal equilibrium. So this is thermal equilibrium, and chemical equilibrium means that the composition of the system, if I have a mixture of gases, the density of the gases at each point of the system should be same. If I take a particular gas and put some other gas into that gas cylinder, then for some time there will be mixture going on among these gases, and the system will not be in chemical equilibrium. There could be reaction or anything can happen. The system will not be in chemical equilibrium. So equilibrium means that we need to ensure all these things. Now the problem is that, try to understand the problem. Now the problem is that if we want to perform, if we want to take a system from an initial state I to a final state S. Okay, so I need to change this thermodynamic coordinates of the system. But as soon as I try to change the thermodynamic of the system, thermodynamic coordinate of the system will go to a state which is in inequilibrium state. Right? And thus when the system is in inequilibrium state, I cannot define thermodynamic coordinates, so the macroscopic description of the system fails. Those systems will not be a thermodynamic system. And thermodynamic description for that system is not possible. For example, let us take the example of that gas cylinder. So let us assume that the volume is V and the pressure is P, so PV, and the temperature is T. This is in thermal bath. Everything is fine. Now I put another weight here. So I put another weight here. So volume will change to some, say, PI, and TI, say it's in thermal bath, so temperature is not changing. Pressure will go to PS, volume will go to VF, and temperature will go to itself. So the system starts from volume VI, goes to volume VF, there is a displacement, so some work has been done on the system. So we are talking about the work on the system, so this is important to discuss. So some work has been done on the system. The pressure is changing from PI to PF. And this is the equilibrium state, this is the equilibrium state. But when the system goes from this initial state to final state, in between, the system is not in equilibrium. This is clear, right? The system is not in equilibrium. Because in between, there is when you put new weights on the system will be compressed, the molecules, it is the gas system, the molecules will rattle around each other. There will be non-uniform pressure, non-uniform volume, non-uniform temperature, and everything will happen. But the problem is for such kind of a system, we cannot calculate how much work has been done. Right? So in order to calculate the work, you need to know exact value of imbalance in the force. You do not know the exact value of imbalance at each moment of time during this inequilibrium state. Because during the inequilibrium state, your pressure of the system is not defined. At this point, you know this is in equilibrium. This is the force acting on the system. Pressure is giving upward force on the piston. In this point, you know, but in between, when the system comes from this initial state to final state, in between, what is the pressure, what is the imbalance in the pressure working on the system, working on this piston is not known because we cannot define pressure. So you understand the problem, right? So the problem is that if the system is in inequilibrium state, we cannot have thermodynamic description. This is the first problem. The second problem is that if I want to change the state of a system, I need to go through some equilibrium state. Obviously, I have to change as soon as I change some parameter, as soon as I change some coordinate of the system will go to inequilibrium state. So I have to come up with some idea. So that idea is the quasi-static process. Quasi-static process means that whenever you change a coordinate of the system, you will change it infinitesimally. You will change it very slowly and infinitesimally, so that the system will go to an equilibrium state, but that equilibrium state is always infinitesimally closer to an equilibrium state. To understand the statement, right? So the point is that I cannot put a big block of mass here suddenly. What I can do, I can obtain this block, this mass here, but put the masses on this piston slowly, small amount of masses at a time, so that the system goes to an equilibrium state, but it is very close to the previous equilibrium state. So that with some approximation I can define the macroscopic coordinate of the system with that we associate the macroscopic coordinate of the system with some equilibrium state. So this is important. So this is how you should go, you should change the thermodynamic coordinate. You can obtain a finite amount of change in thermodynamic coordinates by doing an infinite number of infinitesimal transformations. Okay, so this is the definition of quasi-static process. In quasi-static process means that I am changing the state of the system from an initial state to a final state by means of infinite number of infinitesimal transformations. So this is the definition of quasi-static process. Whatever process in the thermodynamics you will be considering, all of them will be quasi-static process. Because in order to describe the system, we always need to have a well-defined macroscopic variables, and that can only be defined for a system which is in equilibrium or for an equilibrium system which is infinitesimally close to an equilibrium state. Okay, so this is the definition of a quasi-static process. The what we will be going to calculate next will be calculated in the framework of this quasi-static process. We will be calculating work for different thermodynamic systems. Let us assume start with the simplest one, that is a hydrostatic system. System of gases. There are some weights. These has some volume V, some pressure P, and area of this piston is A. So the force acting on this piston is obviously P times A. Okay. and say this length of this gas is L. So volume is V is equal to L times A. Okay, this is the setup. Now I put an infinitesimal amount of weight here. Very small amount of weight here. Then what will happen? There will be imbalance of external and internal force, and the piston, as you can understand, the piston will come down. So let us assume that the displacement is delta x. Okay. So what is the work done? Infinitesimal work done. D cross W. I will come to the meaning of this cross sign later. So the infinitesimal work done can be written as so this is the pressure acting on this system. The external force, as I told you that the convention of sign is that if the external force and the direction of displacement is same, then we consider that as a positive one. Okay. So in this case, the external force is acting in this direction, and as I draw the picture, I consider the displacement in same direction. So this is a positive one. So this is the force acting on this thing, and the displacement is dx. Okay, so d cross w p dv. A times dx is dv. Okay, so this is how you can calculate the infinitesimal work done on the system. Now there is a convention. So now you see, I mean, what is the value of dV in this case? dV is the change in volume, right? So in this case, the volume is decreasing. Okay. So in this case, the volume is decreasing. So dV is negative. So this is how, I mean, this is the convention. How you define your dV? So d cross w equal to, sometimes it has been written as minus pd. I mean, it depends on convention. I mean, once you have chosen a particular convention, you should be you should follow that convention, and everything will come correct. Okay, so this is how you choose your convention, and this is sometimes, I mean, in this book actually I think this convention is followed. The d cross w equal to p dv. So if dv is positive, that means system is expanding. That is the work done by the system. That is negative. And if dv is negative, that is system is going down. Work done for the system on the system. So that work, if dv is negative, that work will be positive one. So this is how you can calculate differential work done on the system or by the system or not. So this, from this differential formula you can calculate, you can actually calculate if a system is in a state I and goes to another state S, initial state I to final state S, what is the finite amount of what you will have to do on the system. So that will be nothing but simple integration of initial state I to final state F P dV. You need to do this integration. Now the question is how this pressure varies with volume, right? So there is this coordinate space. There are two coordinates. One coordinate is pressure, another coordinate is volume. So this is my initial volume, and this is my final volume and pressure. So there are several paths that connect these 2 points. The value of this work In order to find out the value of this work, you need to integrate this integrand over a particular path. Okay, so you understand the point, right? You need to integrate this integrand over a particular path because P equation may not really depend on the volume V. It may be a function of the volume V. That is actually given by this path. What is the path the system is following? So I am taking a system from an initial state to a final state. I can choose, I can vary its pressure and volume. Initial state is defined by a particular pressure and volume, final state is defined by a particular pressure and volume. I can change the pressure and volume in different paths. So I can take the system from here to here, then here to here. Infinite number of paths is possible in which I can change the pressure and volume. The question is that what is the work? The amount of work will be given. Finite amount of work will be given by integrating this integrand over the specific, over the particular specific path. So I do not know. Have you done these things in your mathematical physics course? Integrate on a specific path.
Not in this course, but we have had such courses earlier also. We know.
Yeah, we have some idea about that, right?
Yes.
So that would be easier for me. Okay, so let us stop at this point today. In the next class, I will do some example on. I'll calculate some particular example of work done when a system goes from initial state to final state. Then we go to the first law of thermodynamics and try to understand these consequences. This is important. I mean, this is one of the major part that you need to be able to calculate work done by a system or on a system on a given path. Okay, so there are several examples and questions in this book. In the next class, I will calculate few of them. I'll start from here and calculate few of the examples, whatever. So I have set the conventions and all other things. In the next class, I will do that. Okay. So any questions? Anyone have? Okay, so I am going to follow the sign convention of this book, of this thermodynamics book by Zielinski and Diekman. So that convention I am going to follow. So there should not be any confusion if you understand that convention clearly. Anything anyone want to add or ask or any comment, anything? Okay, so if not, let us end this discussion, and you are supposed to read these two chapters and do the exercise of these two chapters. Okay?
Thank you, sir.
First and second chapter of thermodynamics with exercise. So this is your work for this week. Okay, so see you in the next Sunday.
Thank you, sir.